In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about the introduction to radio frequency module in computer multiphysics simulation software. Now I want to go to the geometry sequence. In global definitions, parameters were in charge to prepare for drawing the circulator geometry. Once the geometry is created, you can then experiment with different dimensions by changing the values of SC chamfer and SC ferrite and running the geometry sequence. These step-by-step instructions build the same geometry that is contained in the application library for Lucy circulator 3 dimensions geometry imported in the section geometry. The geometry is built by first defining a two-dimensional cross-section of the three-dimensional geometry in a work plane. The two-dimensional geometry is then extruded into three dimensions. Note that repeat the modeling steps in page 20 until 21. You need to complete the first two sections, model wizard and global definitions parameters, before defining the geometry. Here it is mentioned that you can refer to the page 20 and 21 for which is related to this article, because you need to regenerate geometry and repeat the geometry with the this sequence geometry. And I want to mention that I will put and I will upload these articles which is from the Council Multiphysics helps document to my GitHubs with exact this name, Introduction to Radio Frequency Module.pdf, and you can search it in the address bar and find it. And finally, you can go to the page 20 until 21 in order to generate the geometry, because now I want to talk about the geometry sequence in this section. Start by defining one arm of the circulator, then rotate it twice to build all three arms. Rectangular 1 in the geometry toolbar, click work plane. Under work plane 1, right click plane geometry and choose rectangle. Go to the setting window for rectangle. Under size, in the white text field, enter 0.2 until 0.1 divided by 3, multiply by square root 3, and the next section in the height text field, enter 0.2 divided by 3. On the position in the XW text field, enter minus 0.2. In the YW text field, enter minus 0.1 divided by 3. Click the build selected button. Note that to turn the geometry labels in the graphics window in the model builder, on the geometry one, select work plane 1 and then select plane geometry. Click the view to node. Go to the setting window for view and select the show geometry labels checkbox. To rotate one, right-click the plane geometry and from the transform menu select rotate. To select the object R1, move the mouse pointer to the graphics window and hover over the rectangular R1 so that it turns red, and click. Go to the settings window for rotate. Select the keep input object checkbox in the input section. Under rotation, in the angle text field, enter 120 and 240. When more than one angle is defined, the operation will create the rotated copy for each angle specified. Click the Build Selected button and then click the Zoom Extents button in the graphics toolbar. The geometry should match the figure so far. Next, build a central connecting region. Circle 1, right-click plane geometry and choose circle. In the settings window for circle, under size and shape, enter 0.2 divided by 3, multiplied by sqrt 3 in the radius text field. Click the Build Selected button and the difference 1, right-click plane geometry and choose booleans and partitions, then select difference. Select the object C1 only to add each to the objects to add list in the settings window for difference. Go to the settings window to the left of the objects to subtract section. Click the activate selection button. Select all three rectangles by clicking each rectangle in the graphics window. Select the keep objects to subtract checkbox at the bottom of the difference section. Click the build selected button. The geometry should match this figure so far. The remaining of the cross-section is generated using geometric parameters along which rotating and rotation, scaling, and linear operations. Rotate 2 in the model builder under work plane 1, right-click plane geometry, and choose transforms. Then select rotate, select the object reference 1 only, go to the settings window for rotate under rotation angle in the rotation text field, enter 180 degrees. Click the Build selected button. It's now time to apply the first scaling for the impedance matching. Scale 1, right-click plane geometry and choose Transforms and then select Scale. Go to the Settings window for Scale under Scale Factor in the Factor text field. Enter SC underline chamber ferrite, one of the parameters entered in the Step Global Definitions parameters. Select the object rotation to only. Select the Keep Inputs Objects checkbox in the Input section. Click the Build selected button. In a Union 1, right-click Plane Geometry and choose Boolean Operations Union. Select the objects R1 and rotation 1 and rotation 1, 2 and scale 1 only. Use the selection list to select the objects if required. Go to the Settings window for Union in the Union section. Click to clear the Keep Interior Boundaries checkbox. Click the Build selected button. The geometry should match this figure. Next, apply the scaling for the ferrite region. Scale 2. In the model builder, right-click Plane Geometry and choose Transforms, then select the scale. Select the object rotation 2 only. Go to the Settings window for Scale under Scale Factor in the Factor text field in the Scale ferrite. Then go and click in Build selected button, extruding the 2 dimensions cross-section into 3 dimensions solid. Geometry finalizes the geometry. Now I'm going to go to the extrude 1, right click work plane 1 and choose extrude. Go to the settings window for extrude under the distances from plane in the associated table enter 0.1 divided by 3 in the distances based on the meter column. Click the build selected button and then click the zoom extends button in the graphics toolbar. From union in the model builder, click from union fin in the settings window for form union, click build up. The final sequence of geometry nodes in the model builder should match the figure. The last steps finalize the geometry and turns it into a form suitable for the simulation by removing duplicate faces. For example, it is performed automatically when material is added for when physics features are defined, but it is good practice to perform it manually as any error message from this step may be confusing when appearing at a larger stage. The geometry should match this figure. Note that if you skipped this section to learn how to create the geometry, you can now return to the next tutorial steps as a material. Thank you so much for watching my tutorial video until the end. Also, you can download the related and the proper computer physics physics simulation file from github.com/masterscape. Today is 28th of April 2026. Time is 12:52 a.m.